Hello and welcome. I hope you've had a lovely day. It's great to see so many of you at the meeting and on Zoom. I'm Alan Willison, and it's my pleasure to welcome you to this meeting of the Hartford Astronomy Group. Just a quick word to those of you at the university to say, could you please make sure your phones are on silent or do not disturb or turn them off so you don't disturb anybody. And I'm sure you've probably found where the toilets are just outside the building. If the fire alarm goes off, please gather sensibly in the car park outside so that we can check everybody is safe and sound. We're not expecting to practice the alarm, so if it does go off, then it will be for real. For those of you on Zoom, if I can ask you to stay muted, keep your fingers away from the space bar because that will turn your microphones on. The format of the evening is after my introduction here. We'll pass over to Jerry, who's going to talk to you about an exciting venture we're considering doing. After that, we'll pass over to Martin, who's going to talk to us about things in the night sky, things which are either live now or will soon be coming up. Following that, Jerry will introduce tonight's speaker, and I'm sure that it's going to be an absolutely fabulous talk that we're going to listen to. And following that, just a few closing remarks from myself, and we would aim to finish around about 9:45. For those of you at the university, there will be opportunities for you to ask questions, but please, can I ask that you wait to the end of the presentations before you ask the questions? That is courteous to the speaker, and of course, it also gives people a chance to pass a microphone over to you so that those of us on Zoom will be able to hear what you're talking about. On Zoom, if you wish to ask a question, then please use the chat facility, type your question in there, and we'll make sure that it gets heard. Okay, so I just want to add one more little announcement before we get going, and that's to remind you that next week at this time, it's our AGM on the 17th of May, not the 19th, if you spotted that on the newsletter, that was incorrect. It's the 17th, and we hope that lots of you will be able to come along and tell us what things you like, what things you don't like, what things we're doing well, and what things we could do better. Be careful, though, you might end up with a job on the committee. Okay, without further ado from me, I'm now going to pass you over to Jerry at the university.
Right. For those who don't know me, I'm Jerry Stone. I'm the Programme Secretary and Publicity Officer for the Society. I arrange our monthly speakers, and I actually do a similar thing, although not monthly, for the Federation of Astronomical Societies, which is the national body that supports all of the societies around the UK. And the main thing I do for them is arrange their annual convention, which I set up to be in a different venue each year. So I started doing this a couple of years ago, and that was at the National Space Centre in Leicester. Last year, our theme was Women in Astronomy, and I was delighted to be able to get Jocelyn Bell Burnell, who discovered pulsars back in the 1960s. And we usually have 4 or 5 speakers through the day, a buffet lunch, and rather nicely, we've been able to do that at quite a low price. We're able to do that for that reason last year because the head of physics at the University of Oxford, and we were there because Jocelyn is based in Oxford, he donated the use of the lecture theatre to us, so that didn't cost us anything. That was really good. So a few weeks ago, I thought, well, what about doing something similar for the society? and it would be fairly local to us. And again, perhaps 4 or 5 speakers, lunch, but also if we site it appropriately, we could then have a break from about 5 o'clock and then do some observing in the evening. So the question is, where might we hold that? Well, one possibility would be here, because we probably wouldn't have to pay for that, although being the weekend, we probably would have to pay for staff. And also, I think we might have to book a lunch through the university events side, and that could be expensive. Another alternative is the Bramfield Village Hall, which is where we held the My Telescope Doesn't Work event. The hall manager there has been very supportive of this and has said that if we were to book that, we could have the hall for the day at the residence rate. So it would only be £125 rather than £165, which is quite something. But also, they'd normally make a separate charge for the use of the hall in the evening. She said she wouldn't do that for us, which doesn't mean we can't use it. It means we can use it, but she wouldn't charge. So that's excellent. And it's out in a nice open area without much in the way of local lights. So that would be something. Also, there is officially a pub literally on the other side of the road. However, when I called them to ask about them providing the buffet lunch, they said they're actually closing down in June. But at the moment, they don't know whether that's a permanent closure or whether they're just going to be taken over by someone else. So they said, call back in June and we'll let you know. Okay. There is one final possibility, and that is to be at Bayfordbury. The advantage there is that, of course, we have the telescopes there, which people would be able to use. The thing is, we would need support from the university, and that will probably have to be paid for. So I'm still waiting for word on that to get confirmation of the total cost. So meanwhile, I have produced a sample budget for the whole day, taking into account cost of the venue, expected cost for speakers, for travel and charges that they might do. And I've been able to set this out so that we would only probably need to charge members £10 for the entire day, including the buffet lunch, which is quite something. And so we would provide scopes. We would ask anyone coming along if they wanted to bring scopes for the evening as well. And the date I've chosen is Sunday, 22nd of October. Now, the reason I've chosen that rather than Saturday is because on Saturdays I have my dialysis session over at St Albans, and that's actually in the evening, but even if we switch that to earlier in the day, it would still clash with the event. So I know that the village hall is available that day. So there we go. There's a one-off thing. Yes. One-off thing, yeah, this is just a special thing. It will not be live streamed. The idea being that if you're interested in it, you need to be there, right? So with the last newsletter, there was a section in that about this saying, if you are interested in this, then click this bit, and that goes to a page that says, I am interested, and this is how many people I think might come along. It does not commit you to anything. You don't have to pay anything at this stage. It's just to get an idea of how many people might be interested in coming along, so that we can go for a suitable venue. If it's not that many, then perhaps we can go for Bayfordbury. One thing about Bayfordbury is we can't use the main the main lecture room, because that is signed out to some other organisation. So we could use the room downstairs to the left, to the right as you go in the main door, but that will only hold about 60 people. If it turns out that we think that that's enough, then yeah, we could go for that. Again, it depends on what will be charged to use it. So the village hall, the manager said that will hold 80 people, which is good, except that when we discussed it in detail, she said 80 because they've had quizzes there with 80 people. But that has been with people seated at tables. If we didn't have tables, then we can have 100 people there. So we do need to know from people, are you interested? Yes. So I'm targeting this at 3 groups. The society members and those on our email list. The local people to Bramfield. So for My Telescope Doesn't Work, they sent out leaflets to all the local villages, and about 15 to 20 of those people came along. And the third team that we'll be particularly after is students at the university. So, as I said, we'll be looking to charge £10 for the entire day for HAG members, £5 for children and for students, and £15 for members of the public. So, does anyone have any questions? Yes.
Will this be advertised in all the local papers?
Everywhere.
Local radio and all that?
Yes. We're hoping to be able to get an answer and decide on the venue by the end of June at the latest. And
might get people joining the society just so they can come to this event.
Exactly.
Yeah.
Yes. Because they pay £10 and yeah, they'll get a £5 discount. Not just yet. We need word from the university about costs for Bayfordbury. And
Does that include the Patrick Moore building and the main building?
yes, yeah, because we'd be probably using that during the evening.
Oh, especially if it's cloudy.
Yeah.
It's be indoors, isn't it? Or
Yeah.
rainy.
But as I said, most of it will be in the lower meeting room,
In
just
the main building.
in the main building, just as you go in the main door.
If it's not a clear night, you've got to do everything.
I know. Yes.
Planetarium shows and
Yes.
things. Yeah.
Of course, we can. We may be able to go and look at the telescopes, and to let people see what they're like, even if we can't actually use them.
You need to repeat the comments from the people here because
Okay.
Zoom comment.
Right. Yeah, so that last question was about using the Patrick Moore building. Yeah. Okay, any other questions? Well, in that case, can I just generally ask, for a show of hands, who thinks this is a good idea? Whoa! That's what I like. Okay, well, as I said, there is a thing in the newsletter about this, and it does ask you to click on the bit that says I'm interested. If you would please do that, that will produce a listing of people that I can then reply to. Okay, thank you very much indeed. That's very encouraging. Okay.
Sorry, Jerry,
Yes.
is the link on the home page of the website? Just because I can't find the, or can it be put there?
I think. Oh well, as I said, it's on the newsletter.
Sure, we can probably get it on.
Yeah. Well, no, I think Alan said he was going to put it on there, up the top right corner, which is where the link for my telescope doesn't work, used to be. So it'll be obvious. Okay. Right, thank you very much. Now going to pass over to Martin, who's going to give his guide to the night sky.
Hi everybody. Just see if I've got, yeah, brilliant. Perfect. Can everybody see that and everybody hear me? Right, I'm going to try and keep this fairly short because I don't want, obviously we've got speaker coming on tonight and we on a limited timescale, so this is going to be a concise talk. So mainly this time of year we've got another meteor shower coming up, which is the Acharids. And they're going to be quite low down because they're coming from Aquarius, which is more visible in the southern hemisphere than it is here. But I've got some information there on there. So active, they're active now, but up to the 27th of May. But peak on the 6th of May, which we've already passed. But then we haven't had many clear nights to actually do much visual work at all. So, but they'll still be around to the 27th. And they're expected to be as many as 50 metres per hour. Okay, so yep, that's in the northern hemisphere. It's going to be quite low down, but if you can get out and have a look, get a clear night, do so. I think it'd be quite interesting. Okay, it's galaxy season, so what it really means is that as the summer comes on, our viewpoint comes more facing out from the Milky Way, looking out. So our main point of view for this time of the year is galaxies. So I'm going to just do a little brief talk about that. Galaxy season in springtime, hemisphere marks galaxy season. So I've just shown a little picture there, Sombrero Galaxy, which is always quite difficult to see because it's quite low down, but not something you can just see with an ordinary telescope. Now, these galaxies just appear as fuzzy blobs normally, but if you've got a camera and you can attach it to your telescope and you can do a reasonably long exposure, you should be able to see something with it. But that picture there was taken and actually won one of the prizes in Photography of the Year 2022. So it's a beautiful picture. So called the Sombrero Galaxy because in its appearance it looks a little bit like a sombrero hat. Okay, so I just put this picture in. I saw it was a picture that of the James Webb Telescope took of Uranus, and it just shows you the power of that telescope. The rings and the colour is absolutely superb. So so the image was taken, I think, not very long ago. Wait, I think it was taken this month, if I remember right, in the information I was reading there. But they're finding out lots more information about Uranus they didn't know. But the colours normally appears very pale blue, but much deeper colours in there. I think it was a fantastic picture. So I'll put it in. So this was quite an interesting piece of information about another potential astronaut coming from England, or coming from Britain, Northern Ireland to be more specific. Rosemary Coogan is on the astronaut training program at the moment. So she will be, if she does obviously go into space, will be the third British astronaut. Obviously, Helen Sharman was the first, and then we had Tim Peake. So yeah, we're looking, about time we had another astronaut up there. So that looks quite a promising thing coming along. Another interesting bit of information. Venus has been very predominant in the skies, and I talked about it last month. It's still very, very bright, still very visible in the evening, especially when the sun just goes down. But this picture here I found very interesting. It was taken by NASA, and it's just showing the volcanic activity on the surface of the planet. So these spots you can see here are actual volcanoes. I didn't realise just how many volcanoes, how volcanic it is. But Venus is very similar to the Earth in as much as its size and its composition. Obviously, it's got a much hotter atmosphere than us, and so obviously not suitable for forms of life like us, but they are still searching for different forms of life there. I know they found amino acids and things like that in the atmosphere. Quickly moving on. So I'm gone on to some images that our astronomers, astrophotographers have been taking. So this was a beautiful picture taken by Steve of the Whirlpool Galaxy. And I've used his narrative on here, so I'm going to just read that. High clouds through the night sky, night during a nearly full moon proved challenge, but 3 hours and 2 minutes exposure on the Pinwheel Galaxy proved worthwhile. And my best capture of this galaxy so far this year, M101, is 21 million light years from Earth, and it's a massive galaxy. It contains 1,000 billion stars, estimated twice the number of stars in our Milky Way. So he's captured that on his Celestron Edge HD8 telescope with a 0.7 focal reducer, his ASI 1260 colour camera, CMOS camera, and Antilla RGB filter. Nice picture, Steve, well done. Again, another picture of Steve. He's very much into his solar photography. This is a beautiful picture of the sun. You can see it's quite active at the moment. And he's talking about the 2 captures of the sun this month, showing the full solar disk of our current very active sun, the cause of many spectacular aurora borealis, sighting recently as far south as Devon. But that's a wonderful image. And a close-up image here, a section active sunspot AR3288, which had an unstable delta class magnetic field with X class solar flares. This sunspot caught the attention of scientists warning about possible of a CME, or coronal mass ejection, that apparently threatened satellites and telecommunications on the Earth last week. Another one, Steve of the Moon, spectacular picture, brilliant detail there. One of his favourite targets, the Moon captured last week, the tiny and relatively young Messier's impact crater, and both all about 10 times 10 kilometres and 1 kilometre deep. Being theorised that the impact happened at a very low angle, causing a rebound and impact of the impact body. To capture detail in these craters is a real challenge, and test the seeing conditions and good telescope collimation. But not all Steve's pictures, I can promise you. So here's an image from Michael, who's taken another picture of the Moon. And he said they managed to get a few minutes of the Moon between clouds yesterday, just 80 frames stacked with Canon M5 and an 8-inch Meade SET with a 0.63 focal reducer. It's a different image by Kevin Noble. This is a Horsehead Nebula, which is probably the most photographed nebula in the night sky, but he's done a brilliant job of bringing the colours out in this. So there's a bit of information about that. B33 Flame Nebula also, which is just below the Horsehead. The Horsehead is a dark nebula made of opaque obscuring dust, which blocks the light from the nebula and the stars behind it. It is located 1,500 light years away. The Flame Nebula, approximately 1,000 light years away, glows because nearby stars are releasing ultraviolet light that causes hydrogen in the nebula gas cloud to lose an electron. When the electron recombines with hydrogen, it releases light as we see it. And this is one of mine. So this is the famous M1 or Crab Nebula. I've reprocessed this a little bit just to bring a bit more information out. So I've put a little bit of information about that particular object. A rapid spinning neutron star, the ultra-dense core of a star that's exploded, is embedded in the centre of the Crab Nebula. Electrons whirring at nearly the speed of light around the star's magnetic field lines produce the eerie blue light in the interior of the nebula. The neutron star, like a lighthouse, ejects twin beams of radiation that make it appear to pulse 30 times per second as it rotates. Image from my back garden, Astro Yard. And that's it.
So, on to tonight's speaker, making his way to the front there, Dr. Oliver Shorttle from Cambridge, who's just come down tonight by train and bicycle, I should mention. And he has, if I remember correctly, he spent most of his time at Cambridge covering a range of subjects, and in order to save time, I'll just say that I was quite surprised when I saw what Oliver had suggested he talk about: rocky planet atmospheres in the solar system and beyond. Now, in the solar system, we have the Earth, Venus, Mars. Those are the rocky planets that have atmospheres. But rocky planets circling other stars, they're not so easy to spot because they are much smaller than the gas giants that we can see. So I think this is going to be quite interesting, and I'm really looking forward to hearing all about it. So over to you, Oliver.
Oh, that's right.
There we go. Okay? Yes. Great. Cool. Well, thank you so much for the invitation. It's fantastic to see those images you shared with us, Martin. Thank you so much. Really spectacular and inspiring. I'm afraid my day job doesn't produce anything quite so beautiful in the talk, but we'll borrow images from elsewhere to try and make it a little bit more exciting. So my background is as an earth scientist. That's where I gained my PhD. But I now find myself working between the Institute of Astronomy and Earth Sciences in Cambridge. And what motivates this, of course, is the discovery of planets elsewhere in the galaxy, or certainly in the nearby galaxy, and the desire to understand those objects beyond merely their detection, but actually begin to characterize them as geological entities. And ultimately, that really is part of the quest for understanding whether they harbor life on them, is to first characterize them as lifeless worlds before we can begin to think of them as potentially life-bearing worlds. So just to begin with, and obviously the atmosphere of a planet is the sort of cradle in which life would likely exist, certainly any life that we could hope to see. And so that's the kind of logic for the talk, focusing on the atmospheres of rocky planets, because it's the atmosphere through which we're going to see life if it's present, but it's also the atmosphere which sets the conditions in which life could hope to be present, say kind of temperate conditions on the surface. So ultimately what we're trying to do in the kind of research we're undertaking is to kind of identify the processes that underpin habitability. So the phenomena occurring on a planet that enable it to host life. And there's a whole series of events and processes starting right from the birth of a planet, so its formation, all the way through to billions of years into its history, which are essential for both establishing and then maintaining habitability. And so I've just kind of listed those here, thinking about how planets gain elements in the first place. Is there a pointer of any sort here?
No.
No. No, that's all right. Maybe I can use a mouse. No, I can't do that. That's all right. Yeah, so from the acquisition of elements, so in the context of wanting for life to be on a planet, we're going to need carbon, hydrogen, nitrogen, those elements out of which life builds itself, but not too much, because then obviously you end up as a kind of thick planet with a thick gaseous envelope. So there's got to be just the right amount of these ingredients. How they're distributed in the planet, and we might come back onto that later in the talk, and then how the early conditions of a planet establish themselves, its early climate. It needs to be warm but not too hot, not too cold. What I've called here prebiotic potential, so the prospect of the planet having the chemical conditions at its surface amenable for geochemistry to turn into biochemistry. And so life initiate. And then kind of running forward in time. So this talk is going to focus on this kind of middle block here of the early conditions on a planet, particularly thinking about how the climate and this so-called prebiotic potential can be established. How can the chemistry of the surface of a planet be set up such that it's amenable for life emerging on it, which may be quite different chemical conditions to what's required for life to then persist. Certainly the conditions that life could emerge in are not the conditions we find ourselves enjoying today, as one example. But before kind of going into the detail, I thought it's useful just to kind of to pull back and understand what's the broader value and opportunity presented by exoplanetary sciences for Earth sciences, or what I'm calling here geosciences. Yeah, so there's many problems, outstanding problems in the Earth sciences about the operation of our own planet. That a whole field, a whole community have been working for some time to try and understand, and myself in my academic career have also worked to understand the processes operating on Earth. But it remains a challenge to understand some key bits of Earth's own history, in particular how it maintained its habitability, so kind of temperate, mild conditions at the surface of the planet for so long, and how it established that particular climate state in the first place. And one basic problem presented by Earth is the lack of information we have going back in time. So this graph is illustrating geological time. So we're at the far right-hand end, and time is running backwards to the left. The planet's 4.5 billion years old, so 4,500 million years old, so off the end of the scale here. And what's plotted on the y-axis is just the amount of rock that there is. And you can see what's happening is, predictably enough, the amount of rock of a certain age is diminishing precipitously as we go back in time. And essentially, this is the geological kind of event horizon lies about here, beyond which there is no sort of material or direct material record of the Earth's earliest history, its first billion years. So that's a really critical period of time in which life likely emerged on the planet. In that sometime in that billion-year window. And earlier on, even going even further back, is when the planet sort of transitioned from its presumably hot early state into a temperate world with oceans and things that life is then subsequently taken for granted and exploited. So this problem of missing information, one opportunity that other planets present, whether it be Mars, Venus in the solar system, or exoplanets, is an opportunity to fill in gaps in time of a planet's history by observing them. And Mars is a fantastic example of, in the solar system, an object which potentially allows us to reach back earlier into the history of planets in our solar system to gain some insight into what's going on. The second point is diversity. So here's an image of Earth and Venus next to each other. The solar system harbours a fair amount of diversity of rocky planets. I mean, Earth and Venus being good examples, but we can sort of think on that spectrum, really thinking out to Pluto. It's a amazingly geologically active object in the solar system, and Mercury also. But that said, there's still a limit to the diversity that is present. And in the context of exoplanets, what's been striking is planets that are maybe 2 to 3 times the mass of the Earth, that exist in this intermediate regime between the much more massive planets in the solar system, Uranus and Neptune, so 10 times more massive than Earth. That kind of gap in the solar system between Earth and Uranus and Neptune isn't occupied by anything, but in the galaxy is commonly filled by so-called super-Earths. So those planets represent an exciting opportunity to understand physics and planets in extreme conditions, which we're never going to get studying the solar system. So what are exoplanets offering us? They're offering us the opportunity to time travel. So I'm sorry, the text is, oh, thanks. And this is just, there's this nice cartoon I like using from Chris Ballantyne in 2002, published in one of his papers. And what we're seeing on the left is Earth kind of imagined just after its formation, a giant molten ball in which large impacts are still happening into this partially solidified surface. There's maybe material still falling through the planet to form the core which today obviously gives us our magnetic field. And at some point, somehow, the planet transitioned to what we see on the right, another cross-section through the Earth, but now exhibiting those processes which have operated for at least the last probably billion years, of subduction, magmatism at mid-ocean ridges, the sort of geological processes we see written on the face of the modern Earth if you look at a topographic map of the planet. And how this happened, how this transition from molten ball to habitable planet took place, is incredibly hard to reconstruct just from the information we have available on Earth, because this bit of the history is lost to us. There aren't rocks or anything else we can really directly pick up to tell us about this evolution. Yet exoplanets, some at least, may be trapped permanently in a molten state. And this is a graph looking at the radius of a planet in units of Earth radii. So this is 1 Earth radius, 2 Earth radius. And looking at how much light they receive from their host star. So this would be the same amount of light as Earth, and then 10 times, 100 times, 1,000 times, 10,000 times more light. And the key point in this figure is that many of the planets that have been discovered, or at least that are illustrated here, they all lie far to the right of where Earth lies in this diagram, which would be just around here, in a region where they're much more irradiated by their host star, The result of which is that some of them have extremely high surface temperatures and maybe have been kept permanently molten for their entire lives. So they formed molten and then have been kept that hot for billions of years subsequently by the heat of their own star. And that means that if we study those objects, we can look at a planet in the state of being a magma ocean today. And that's a state that many planets may have passed through in their life. So we can essentially sort of time travel in the history of any one planet by looking at these special cases where they're sustained as molten objects. So that's a kind of exciting area of study in the field. Kind of more extreme, we can obviously go to protoplanetary disks. I think you've had a talk about protoplanetary disks maybe this year. This is TW Hydra. On the left, a beautiful image of the warm dust glowing in TW Hydra. This is a 5 million year old planetary system, so 5 million years after the birth of the star, so reaching right back into its earliest stages of planets still likely forming in this disk of gas and dust around the star. And we can equally go potentially to the other end of the spectrum. So the bright star in this image is the so-called Methuselah star, which estimates of its age place it within error of the age of the universe. So it's a star that's basically, as old as it's as old as it can conceivably be. There probably were earlier stars, but as far as we can tell, this is kind of as old as it gets. We can't estimate its age any more precisely. So this is a star that's over 10 billion years old. So we can go right to the beginning and right to the end in this kind of image. And in principle, that's what looking at planets outside the solar system allows us to do, kind of look at these systems in various states of evolution. And there's also, like I said, there are these fundamental questions that we have about how Earth operates and about how rocky planets operate that are extremely challenging to answer when you only have one planet to interrogate. This is a spectacular satellite image of the Bengal fan you can see mud essentially pouring off of the fan into the Indian Ocean here. And this kind of process, what this is illustrating is the weathering of rock. So they're breaking up of bits of rock ultimately from the Himalaya, and their chemical alteration and the dumping of all of that product from that chemical reaction into the oceans. And that's a key process for regulating the amount of carbon dioxide in Earth's atmosphere. Unfortunately for us, it regulates it on rather long time scales. So it's not a get out of jail free card for us. But it is for the planet. I mean, ultimately, this is the process which brings carbon dioxide levels back down after they've been elevated by whatever process may have raised them. But we don't know exactly how this process works. And we can see that this kind of key mechanism for maintaining a habitable planet, because of course CO2 is critical for regulating the temperature of an atmosphere by absorbing outgoing long wavelength radiation. We know that given our impact on the modern climate, and we can see that this regulatory mechanism is broken in two instances in the solar system. It's broken in the case of Venus, and we saw a really beautiful image of Venus that Martin showed from NASA. It's broken in the case of this planet, whose atmosphere is 97% CO2 and a 90 bar atmosphere, so nearly 100 times more massive atmosphere than Earth, most of which is carbon dioxide. And it also broke in the case of Mars, where now the carbon dioxide is still a major constituent of the atmosphere, but the atmosphere is only 6 millibars, so it's 6/1000th the pressure of Earth's atmosphere, and the carbon dioxide is actually condensing out of the atmosphere in the poles. So in both cases, Earth's nearest neighbours, carbon dioxide essentially plays a key role in the planet's history, but a catastrophic one. It's only on Earth where it's been regulated and the planet's maintained clement surface conditions. So really this process of regulation of carbon dioxide is a really central one for us to understand as planetary scientists, especially if we're interested in understanding how planets remain hospitable to life. Okay, so in the solar system, we can begin asking questions and investigating how planets work, in a variety of direct ways. What I'm showing here is the instrumentation that's in Edinburgh University, that is a mass spectrometer that allows you to probe the composition of materials on extremely small spatial scales. The image at the top is a tiny little pocket of magma that was trapped inside a growing crystal in an eruption from Iceland. And these little pockets of magma contain information about the composition of Earth's deepest interior. We can directly collect those magmas, and we can go to this fancy instrumentation in Edinburgh and measure their composition and learn about Earth's interior. Further from home, we can go out into the solar system and capture these spectacular images. In this case, Io image by Voyager 1 in 1979, looking at this spectacular plume erupting, the Pele plume erupting on the limb of Io there. An incredibly inspiring image. So you can see geological activity elsewhere in the solar system, in this case in a small moon. And obviously there's also robotic missions to planetary surfaces, so kind of doing geological field work, but using robots. And that's what we're seeing here, the Perseverance rover drilling into a rock on the surface of Mars to interrogate its composition. So these are the kind of tools we've got available in the solar system, and all of them are outstandingly better than anything we have available to us, of course, if we're looking at exoplanets, where we're having to deal with whatever light comes to us, and that's all we've got. We have to make do with light. And that light, if we want to interrogate the geology, we're looking for light that's passed through the atmosphere and has been influenced by the atmosphere, and therefore will tell us something potentially about its composition and maybe the geological processes. And there's this really fantastic image, NASA space shuttle image, looking through the limb, the limb of Earth's atmosphere, shortly after the Pinatubo eruption in 1991. So we're seeing the top of storm clouds here. The shuttle's looking side on at the Earth. You can see it's darkening out to space at the top of the image. And there's this fantastic layer in this kind of pink-purple of aerosols, so sulfur gases that have been emitted by the volcanic eruption and injected high up into the atmosphere. So this just emphasizes to me how if we're able to probe these upper layers of planetary atmospheres, we're probing a region which is affected by the geological activity at the planet's surface and the biological activity. So it's this narrow window above the storm clouds on a planet in the tenuous region of its atmosphere where we can try and extract information on that planet's geological and biological processes to infer what's happening and ultimately whether there's life on that planet. And obviously the technique to do that is sadly not space shuttle images of all these planets' atmospheres, but is relying upon those atmospheres passing in front of their host star. And this is a really nice image of the transit of Venus in 2004. We can see the light, the sun's light kind of refracted around the edge of the planet, indicative or suggestive of the presence of an atmosphere on Venus and it not just being a bare rock. And this technique of that light being refracted and passing through the upper layers of a planet's atmosphere, that so-called transmission of light through the atmosphere, is the key technique which will give us insight into planetary processes outside the solar system. So there's three things I could potentially touch on in this talk. I suspect I won't get through all of them, but I'll start with one and we'll see how far we get. So the kind of work we do is principally laying the foundations, sort of theoretical foundations for how we might interpret atmospheres that we observe. And the processes we're interested in thinking about are the role that impacts have on atmospheres. And so here's a kind of artist's impression of a large impactor onto a growing Earth. How does this affect the composition of atmospheres? So this is going to tell us something about the early Earth and its early history, but also something about what we might expect to see looking at other planets if they've been affected by large impacts. Volcanism, we just saw that spectacular image from the space shuttle of the Pinatubo eruption having affected the upper layers of Earth's atmosphere. Planets like Venus, may have entirely volcanic atmospheres. The origin of the whole atmosphere is volcanic. So it's key that we understand what the outcome of volcanism is if an atmosphere has been built by volcanism. And the image there is of the Mount St. Helens eruption. And then Venus as well. So a key question for us is distinguishing when we look at a planet and we see some information, we obtain some information on the composition of its atmosphere, is that we're able to distinguish just at a basic level, are we looking at an Earth-like planet or are we looking like a Venus-like planet? So two outcomes of a roughly Earth-sized planet in its evolution. The solar system tells us there's sort of at least two fates that planet can experience, and it would be useful if we could distinguish between them from the observations we're likely to get with instruments like JWST. So those are three pieces of work, and we'll see how far we get through them. And we're going to start with the impact atmospheres, which is work that's been led by a PhD student at Cambridge, Johnny Itkowitz. And the key question we're asking here is, what type of atmospheres do impacts create? And then to think about the implications of those types of atmospheres. In particular, how does it impact the early climate on planets? And sort of associated with that, how does it affect the likelihood or the possibility of those planetary surfaces hosting useful chemistry that could lead to life, which evidently appears to have happened on Earth. Just to kind of why worry about impacts? Well, we already saw with those spectacular pictures of the moon that Martin, you shared with us, those surfaces are interesting to look at through telescopes because they're ridden with craters, right? A spectacular topography that's been created by milling of the lunar surface by impacts over its 4.5 billion year history. So I just pulled this image, again a beautiful Apollo image from NASA showing the Motkey crater in the Mare Tranquillitatis. So 6 kilometers diameter, this crater. So this is essentially impacts at a small scale. Obviously it would be bad news if something like that hit Earth or hit this lecture theatre. But it's on a planetary scale, it's not a big deal, right? It'd be a big deal for us, but it's not going to transform the chemistry of a whole planet to have an impact like that. The kind of impacts that do really change things, the kind of impact that's inferred to have created the hemispherical dichotomy on Mars. So an impact so large, you almost can't see it for the planet. But Mars, you can see, has a kind of dark-coloured south pole and a kind of smoother red colour to its northern hemisphere. And that is a sort of dichotomy. It's a large-scale asymmetry to the planet's surface, which is inferred to be the result of a large impact, with the southern rocky highlands being the part that wasn't impacted, and the northern plains being having experienced the impact. So there's features on solar system planets indicating that impacts occurred on a range of scales, and of course the lunar surface itself shows cratering on a wide range of scales. So if the lunar surface is recording that, if the Martian surface is recording that, then the Earth itself will also have been subject to large impacts early in its history, which could have transformed the chemistry of the surface environment of the planet. And we can even look beyond the solar system to kind of infer that impacts are likely to be ubiquitous. So this is an image of a very young system, Fomalhaut, 25 light years away, only a few million years old. And there's a narrow ring here, this narrow ring, which is likely sculpted by the presence of planets. But this is a ring of dust and debris left over from planet formation. And this is the kind of reservoir of material which, if it's flung inwards by gravitational interaction with planets, could bombard planets closer into the star, and is the sort of reservoir for extensive modification of small planets that then get this material thrown at them. And we can see by images like this and other astronomical observations allow us to see that the abundance of this material decays progressively with the age of the system. So we're looking out to 10 10,000 million years, so 10 gig a year on the far right. So this debris slowly depletes with time. That's the kind of key point, indicating that it is being ground down and moved inwards in the system. And we also know that this material had to have been delivered to Earth. So Earth's surface today has been transformed by plate tectonics. So the surface of Earth is incredibly young because it remains geologically active. Yet we know indirectly that this late delivery of material to the planet must have occurred. And the clearest evidence for that is the presence of precious metals in rocks, rocks in Earth's interior. The kind of precious metals used to make this beautiful Egyptian statue of Amun-Ra, so gold, silver. And the reason the presence of these metals is indicative of impacts having occurred is because these metals should or have a propensity to move to the core of a planet. So I said the Earth began life as this molten ball, and there were two sort of main components to this molten ball of the early Earth, one of which was the molten rock, and the other of which was the molten metal. And the metal sunk to the middle of the planet and formed the core, and that's what's sort of illustrated here. But in so doing, it took with it many elements that had an affinity for iron metal. So things like silver, gold, platinum, iridium, ruthenium, metals that are precious, metals that have kind of technological use and value in sort of technological applications. Many of those metals would have gone in large abundance to the center of the Earth with the core, and so have been lost to the rocks that we can access at Earth's surface. Yet those elements are present. So how did they stay accessible to us, given that they all ought to have dropped along with the iron to the center of the planet? And this graph is just trying to illustrate the magnitude of the problem. So this red line is what is present in, so what we're looking at is the abundance. The units don't really matter, but it's the abundance of these different elements: rhenium, iridium, ruthenium, platinum, rhodium, palladium, all these elements that should drop out into the core. That red line is what their abundance is in Earth's interior. And all these black lines and grey lines are basically the models, the calculations of how abundant they should be. The details aren't super important, but every estimate says that there should be vastly less of these elements than we actually observe. So the only real explanation for that is that Earth's core formed, took all these elements with it, but then they were re-delivered to Earth in a later event. They were given back to the planet by some giant impact later in its history. So this is the kind of most direct evidence we have for Earth having experienced a major episode of bombardment after its initial formation. So what does this potentially do to the chemical environment of Earth's surface? Well, what's obviously really distinct about Earth in the solar system is the presence of liquid water at its surface. That's widely assumed to be essential for life. We've no idea of how life could exist without liquid water. It's such a powerful and useful solvent. And it's also of significant climatic importance. As I showed with that image of the Bengal fan, water is directly involved in maintaining the climate of Earth on long million-year timescales. What happens if you drop say an asteroid into water is there's a disequilibrium. They react with each other. And a key reaction that takes place is between the water and the metallic iron. And that's what the reaction on the right is showing. And this lump is an iron meteorite that we're seeing, an image from the Smithsonian. So many meteorites contain native metal in them, metal that early humans would have found and worked directly to make tools from. That metal reacts with water and it produces hydrogen gas, which is the H2 on the far right-hand side. And hydrogen gas is extremely reducing, and has significant implications for the climate if you produce a lot of it. So, for example, when this image on the right is Stanley Miller's famous experiment of the shock, putting electric shock through gases to produce amino acids and various molecules that biological molecules or biologically relevant molecules. And so it's a classic example of a prebiotic chemistry experiment. That shock experiment, synthesizing organic molecules in an atmosphere, used this composition of gases at the very top: water, methane, ammonia, and molecular hydrogen. But Earth's modern atmosphere, it contains water, carbon dioxide, nitrogen, and its modern atmosphere obviously contains a lot of oxygen as well that biology's put there. But the key point is that this is the atmosphere we might expect the Earth to have had early in its history, yet the atmosphere at the top is what you'd really like if you're trying to make life out of an atmosphere. You don't really want an atmosphere like this. You probably want one that's much more reducing, like we see at the top. And you can see it's reducing because we've got less oxygens in the species. We've got C8, we've got methane, CH4 instead of CO2. So it's a more reducing set of gases. So where does that hydrogen come from? Well, it potentially comes from the impacts themselves. The second thing to say is that the climate significance of hydrogen is really major. So this is the distance of a planet from its host star, and what we're looking at in these two lines, and let's just focus on the red line, this is for a low mass star, but this is the required pressure of just pure hydrogen to sustain a surface temperature of 280 Kelvin, so a temperature at which liquid water would be stable. So you can have a climate in which liquid water would be stable just with hydrogen, without carbon dioxide or anything else. So it's a powerful greenhouse gas, and even in small quantities it can significantly warm the planet. Okay, so what we're interested in is understanding how important this process of impact can be for changing the surface conditions of a planet by turning the water into hydrogen, and thus making an atmosphere which is more reducing and more amenable to prebiotic chemistry, and maybe also changing the climate. So the simplest thing to do, and this graph again has some funny units, but we don't need to focus on that particularly. The simplest thing to do is to take an impactor of a certain mass, and the mass units here are 10 to the 22 kilograms, and so for reference, Earth is 10 to the 24 kilograms, so pretty heavy. But these are impactors of about 1% the mass of the Earth, so very, very, very large objects hitting the Earth, sort of moon-sized objects essentially hitting the planet. If they hit the Earth, how much hydrogen can they produce? And that's essentially what this axis is tracing, is the bigger the impactor, the more hydrogen that can be produced. So that's kind of a simple calculation to do. And that's equivalent to, as I've written there, tens of bar of hydrogen. So tens of surface pressure, modern Earth surface pressure is equivalent of just pure hydrogen gas. So a wildly different environment to that which we find ourselves in today. However, that's the really kind of naive calculation where we just take the impactor and we just put it at the surface of the Earth and let everything happen that could happen. In fact, as you can probably predict, when something so large hits a planet, all hell breaks loose. You significantly melt the surface of the planet. There's a massive redistribution of material. So this simple scenario is not really what's going on. So we really need to understand, if we want to understand the significance of these impacts on the early Earth and for planets generally, we need to be able to model and predict this process whereby there's extensive melting of the interior of the planet. And so the atmosphere, and this is what was shown here in blue, this very inflated atmosphere following the impact, to what extent does it really interact with the metal, the iron metal of the impactor, versus the impactor actually just sink into the planet and itself become part of Earth's core. So the key question for us is how the impactor interacts with the planet. Like physically, how is that process operating? And so the way we try and address that is using a shock physics code, ISAIL, which is developed by folks in Imperial, for example. Gareth Collins in Imperial develops ISAIL. So it's a code that can predict material properties in extreme conditions, the kind of extreme conditions you get when you throw something the size of a moon into Earth. So what we want to do is simulate those impact events. And this is what we're seeing, like a static frame from such an event here. This is Earth in the model. This is the target, and this is its core in blue, and this is its rocky mantle in grey. And the thing at the top with the kind of rainbow colours, that's the impactor. That's the kind of moon-sized objects that's hurtling towards Earth. And its core is the rainbow part in the middle. And the colours are just indicating where the material is going to end up. So the pink bit of the impactor, that's the part that's going to go into Earth's core. The yellow part is the bit that's going to be vaporised. There's so much energy in the impact that's going to turn to vapour and it's just going to leave the system. The blue part's going to escape. It's just going to directly be flung off into space. So let's see if the video works. I'll try and see if I can rewind the video. Can I do that? I might try play it differently. Yeah, this might work better. Yeah, there we go. Right, so this should be better. So there's the impactor hitting the planet. This is all happening in a few hundred seconds, essentially. I'll try and move through. So the impactor comes in. You can see the surface of the planet deforms dramatically. The core gets smeared out. Some of it ends up in that kind of string of material, that wave of material that's leaving the planet, ends up not being gravitationally bound. But some of it gets decelerated and enters the mantle. So that's the sort of pink and orange stuff now. We can see just at the interface between the black of space and the grey of the planet's rocky part. That material now, some of it's entering the mantle, but this is metal. So this is physically has different properties from the rock and is much denser. So some of it sinks, and that's what we can see in that kind of plume of pink material moving down. That material sinking towards the core of the planet and merges with the core of Earth. So it's just more metal added to its core. And the orange part in this simulation, so these dots that are distributed throughout the mantle, that's the part of the impactor that can contribute to, for example, the platinum that we have available to us today. That's the part that gets left behind and ends up being accessible to us at the present day. I'll just let the simulation run. Okay. So we can look at that another way. You get a sense of how dramatic this is if we look not in terms of where material is going to end up, but the temperature. So this is now the same video, exactly the same simulation, but this is the temperature, a temperature field. So looking at the temperature of Earth, like at this point before any impact has happened, and this is the temperature of the impactor. And the core of Earth is bright white here. It's extremely hot. So I'll just rewind the video again. So let's see the impactor go, and so you can see immediately what happens is all that energy, the kinetic energy of the impactor, gets translated to thermal energy in the Earth. You can see the temperatures are reached in excess of 5,000 Kelvin. So that drives huge amounts of melting of the planet's surface and its interior. It melts all the way to the core mantle boundary, so 2,900 kilometers deep within how many seconds is that? Probably within 100 seconds, or less than that actually. maybe within 30 seconds of impact, you've gone from a planet that, from a nice pleasant Wednesday afternoon to the whole hemisphere of the planet's molten. So that's bad news. But luckily, life probably hadn't established itself yet. So it missed out on the show, but also wasn't wiped out by it. So yeah, you can see we've now melted essentially the northern hemisphere of the Earth. That bright white plume is the metal descending into the center of the Earth, and that's aided by the fact that you've substantially melted the mantle of the planet. That aids in the metal sinking to the core. Okay, so it's these kind of simulations which allow us to predict what the outcome is for a planet of these impacts. So that metal that gets lost to the core is metal that isn't sticking in the mantle. It's not reducing water, so it's not producing hydrogen. So when we model the process accurately, we discover that these impactors are less efficient at producing, say, hydrogen and leaving platinum behind in the mantle than we might naively expect. Okay, let me try and switch back to the other view, actually. That might be better at this point. Oh, how exciting. Yeah, I was trying to be too clever, I think. I think the safest thing to do at this point is just to stick with what works. Let's just do that. Okay. So yeah, we ran lots of these simulations, or Johnny ran lots of these simulations. They didn't all work. Here's a simulation that we possibly got a bit wrong. But luckily, Johnny didn't always do that. So most of the time, the calculations are set up correctly. This remains my favorite one nonetheless. That was a good day. It was just a very bright comet past the Earth. The astronomers had a field day. Okay, so we ran lots of these simulations, and the key things we were varying is the size of the object that was hitting Earth and the angle it was impacting the planet. So the most common angle for an impactor to occur at is 45 degrees. These 30-degree impacts, so they're becoming more head-on collisions. That's what the little kind of cartoon at the top is trying to indicate. That's a more head-on collision. In these ones, almost all of the iron, so this is saying where the iron ends up. And this is saying all the iron ends up in the interior, basically. So all of that iron avoids the surface, goes straight into the center of the planet, and is basically lost. Lost from the surface environment. That stops being true when the impact becomes more oblique, and we kind of saw that in the videos. Some more of that iron gets preserved near the surface. And when the impact becomes really oblique, it becomes like a hit-and-run collision. The impactor comes, causes devastation, and the material is essentially not accreted. It doesn't have the decency to stick around, and it heads off into the solar system to do more damage elsewhere. But most impacts are in this statistically are going to be in this middle case where some material ends up going into the middle of the planet, some iron is left behind at the surface. And what that does is it takes what our initial guess of the outcome was and gives us this line that I've just drawn on now, the solid line, which is showing we get about 10 times less hydrogen as a result of these impact events if we kind of model the physics accurately. So what that tells us is that impacts are important. We know impacts were going to be a major process in the early solar system, which did lead to atmospheres on the early Earth that were reducing, so had lots of methane and hydrogen. But in detail, where the iron of that impactor ends up matters a lot. And so that's what we're still kind of investigating that now, kind of moving forward. Let's see. Right, I think what I want to skip to actually, no, this is okay. I think we can do it. The next question I want to ask is, what does a purely volcanic atmosphere look like? So we've seen what the effect of throwing a huge rock at an atmosphere is. It's to make it really reducing. Another major process is volcanism. And we specifically really want to understand what information does it tell us about a planet's interior. So processes like volcanic eruptions that we see here, Mount St. Helens, they're transferring information from the interior of the planet to its surface. And that's really valuable to us. If all we can see is the atmosphere of a planet, then we've got to read the information on its interior from its atmosphere. And like I've shown this figure before, these hot planets over to the right here are likely to have every chance of being highly volcanically active. So our kind of default working assumption is that volcanism is going to be a major process sculpting the atmospheres of these planets. So what does volcanism do when you build an atmosphere out of it? And this is relevant not just for exoplanets, but obviously the early Earth as well, because like I've stressed, planets, rocky planets are likely to always go through a phase where they're molten to begin with and transition to the kind of pleasant planet we see on the right. And this by being molten like this is essentially just an extreme form of volcanism where the whole planet is degassing, putting volatiles like water and carbon dioxide into the atmosphere from the magma. So Pip, the student that worked on this at Cambridge, Pip built this fantastic computer code to model volcanic degassing. And I won't go into too much detail about how this code works, but something that really mattered or really matters for the composition of volcanic gases is how oxidizing the interior of the planet is. And I've just tried to illustrate that with this reaction where carbon monoxide, if you add oxygen to it, will become carbon dioxide. So just at a very basic level, if a system is very oxidizing, if a magma is really oxidizing, then the carbon that it releases to the atmosphere is going to be carbon dioxide. If the magma is very reducing, then it's going to produce carbon monoxide. And that's obviously what we're familiar with in terms of, combustion and safety if we're having like a gas fire in our homes. If the gas fire doesn't have enough oxygen, then it might produce carbon monoxide when we burn it. And that's obviously kind of dangerous in a domestic context. So that same reaction that we're kind of familiar with in terms of like home safety is important in volcanic eruptions as well. And planets in the solar system are differently reducing or oxidizing. So the numbers don't really matter here. The key thing is that Earth is a very oxidizing planet in its interior. Mars is more reducing. So we expect there to be some variation in how oxidizing the interiors of planets are, and that is going to impact the volcanism that they produce. So there's two kind of outcomes I want to emphasize for when we think about volcanic atmospheres. The first of which is the physical properties of the atmosphere and how that's affected by how oxidizing the interior of the planet is. And the key physical property we want to think about here is the height of the atmosphere. And I thought this is a useful image to come back to because we can see the atmosphere basically decaying to space in this fantastic space shuttle image. We're going to the dark of space up there. So this is giving us an indication of the height of the atmosphere, the length scale over which it decays to nothing into space. And that height changes depending on what the atmosphere is made from. And what we've already seen is that if a reducing atmosphere has more gases like carbon monoxide, an oxidizing atmosphere has more gases like carbon dioxide, and that changes the height of the atmosphere. And it changes it by potentially 100 kilometers or more. And that's what we're just seeing on this graph. These kind of how the atmosphere height changes as you change its composition. And that's important because this is the height of the atmosphere is the kind of thing we're sensitive to when looking at exoplanets. Finally, the atmosphere's chemistry also changes, and so we can classify these atmospheres into different categories depending on their composition. And so the key thing is that these are gases which we can in principle see looking at spectra of atmospheres of planets, and therefore can begin to learn something about the interior of the planet. So we've kind of learned about what a purely volcanic atmosphere looks like. It can tell us about the planet's interior. It affects both the physical and chemical properties of the atmosphere, and so gives us a route into actually making observations of the interior properties of planets just from their atmospheres, even if all we can see is the atmosphere. Finally, I just want to really quickly end on Venus-like atmospheres. So the key question for us is distinguishing Venus from Earth. They're very, as we heard from Martin, they're extremely similar planets in their mass, in their radius, and actually how far they are from our sun. So if we look back at the solar system as if we were looking at an exoplanetary system, it wouldn't at all be obvious that Venus is kind of a hellscape and Earth is temperate and pleasant and has liquid water at its surface. So how can we actually tell them apart when we're looking at them as exoplanets? So Venus has a whole load of complicated chemistry happening in its atmosphere, lots of which is completely alien to us on the surface of Earth, like lots of hydrogen chloride, hydrogen sulfide, sulfur dioxide, so lots of gases that would quite quickly kill us if they were present in high abundances at Earth's surface. Unfortunately, because Venus also has thick clouds, we can't see directly most of that atmosphere. What we're seeing is the very high atmosphere. And in the very high atmosphere, those telltale traces of a sulfur-rich volcanic atmosphere are hidden from us. So it's actually quite hard in the context of Venus in our solar system to look at it like an exoplanet and actually see that it is Venus-like. It looks quite Earth-like when you're restricted to just seeing the upper atmosphere. But the key thing is that actually ends up being, that's an artifact of how bright our sun is. So we want to look at one particular gas, carbonyl sulfide, OCS. What we're looking at is how abundant it is in the atmosphere as a function of height. And the key thing is its abundance is much higher when the star that the Venus is around is a smaller star that's less bright, because the light from the star ends up destroying this molecule so that we can't see it in the higher atmosphere. And these small stars around these M-dwarf stars are the ones we can most easily observe. They're most common stars in the galaxy. They're the easiest to observe planets around, and we get the best data for planetary transits. So the good news is that around these types of stars, which are the ones we're going to be focusing observations on, we can easily tell a Venus from an Earth, because this gas, this key trace gas of volcanism, isn't destroyed by the light of the star. I'm sorry. So we've looked at how we can identify an exovenus, and we can use these trace sulfur species around cool stars to distinguish an Earth from a Venus. Cool. So that's everything I wanted to cover in this talk. We've looked at essentially kind of three key processes that affect planetary atmospheres: impacts early in their history, volcanism that builds the atmospheres, and how we can use the volcanism or the gases that emerge from volcanism to tell apart a Venus and an Earth-like planet when we're looking at exoplanets. And that's the first step to then more deeply interrogating the Earth-like planet for signs of life, for example. And broadly, that's the kind of main aim, is to understand habitability of planets in order that we can investigate them for life. Cool. Well, thank you very much for having me.
Are we on? Yes. Okay.
I appreciate a glass of water.
Oh, yeah, thank you.
It's all right, just because all the questions will be coming. Well, thank you very much, Oliver. It struck me early on that a presentation such as this would have been pretty impossible not that long ago, because we just wouldn't have known enough about such exoplanets. What would you think is the most important thing that has been learned about them?
Yes, that's a good question. I think the characterization, thank you so much. I think learning in detail about rocky planets is is the frontier of the field. That's where we still need to go. And the hope is that the James Webb Space Telescope affords that opportunity to probe the atmospheres of these small rocky planets in a way we've not yet been able to. So I think in the major discovery from my perspective is that these small rocky planets are the most common types of planet in the galaxy. So if what your business is understanding the kind of processes that take place on Mars, Venus, or Earth, then those are the most common types of planet in the galaxy. So that is the most frequent outcome of planet formation is planets of somewhere in the Mars to a few Earth mass range, which means that geology is going to be ubiquitous. The prospect of thinking about diverse climates, diverse geological processes, and maybe diverse life is given a lot of life by that basic discovery that's been made.
Okay. And also, looking at one of your early slides, I thought how interesting that Mars and Venus have such a similar composition of atmosphere, and yet the pressure, 6 bar to 90, is so incredibly different.
Yeah, it's striking how similar the atmospheres are chemically in some respects, and in the major species in the atmosphere, despite the wildly different climates that they have.
Okay, do we have any questions from anywhere in the room?
Yes.
You mentioned early on a star. I can't remember. You call it Medusa star, a very old one.
The Methuselah star. Yes.
Have you found anything like that with planets around it? And is there anything surprising that we've learned from that?
Yes, that's a good question. So I think it turns out to be sort of frustratingly difficult to put precise ages on stars. This is not my area of expertise. So the techniques to, once a star's on the main sequence, it's almost by definition not changing very much. So high mass stars obviously undergo rapid change on the main sequence, but low mass stars change very slowly. So particularly for low mass stars like M dwarfs, their main sequence lifetime can be hundreds of billions of years. So stars that small have never died. They've been born, and the universe is too young for them to have seen out their life. In fact, the age of the universe is just about long enough for a G dwarf to have had one lifetime. That said, there have been attempts to put ages on stars, and I think we're still to really, for the population of stars that are on the main sequence and maybe range in age by maybe 5 billion years over the population, I think we're yet to see any systematics drop out. And partly that reflects probably that those systems are relatively quiescent dynamically. The information we have is just presence or absence of planet and planet size, neither of which are probably changing very much once everything's settled down. All the changes are probably happening within the planets. If you could look at the rocky planet and see how its climate's evolved, then that's where the information is, but that's not where we've been able to reach with the observations yet. So I think the really exciting thing looking kind of back in time has been the observation that planet formation happens extremely, extremely rapidly. So those observations of protoplanetary disks, which often show beautiful ring structure in them, indicates that very large planets are forming extremely rapidly, extremely early on. So that's a really exciting insight that's come from those studies, kind of at the very beginning, is how early planet formation begins. And that combined with observations from the solar system are consistent with basically from the birth of the sun, everything happening in only 3-4 million years. And in that short period of time, you've got Earth, you've got Jupiter, you've got all the planets, and everything's then set up for the next 4.5 billion years, which is kind of amazing.
Thank you.
Hello. Do you think eventually we might be able to leave this planet if it's totally ruined and find another exoplanet? Do you think it's ever going to be possible?
No. Yeah.
No, I don't think so.
I'm not optimistic.
No.
I think if we
So we've had it basically, haven't we, really?
Yeah. I would say if we haven't got it in us to not ruin this planet, we've unlikely got it in us to get to another planet. That would be. But I think we have the ability to not ruin this planet. So I think there's still hope in that respect.
Probably a stupid question.
No, because there are attempts to get objects, to get like spaceships to the nearest, like to get out a spaceship to Alpha Centauri. Well, not really a spaceship, more just like a small, a tiny like microchip, basically, to get it on a huge sail and accelerate it to the nearest star, and you get maybe, I don't know, a fraction of a second before you've shot past it and are on into kind of totally empty space. So people are trying to figure out how to get remote missions to other star systems, but it remains a huge technical challenge. Probably a bigger technical challenge than just not screwing up our own planet. That's maybe a political challenge.
We have a question on Zoom, Oliver. It's from Jeff Bryant. What instruments, telescopes, and sensors have been used to gather most of the data used in this analysis?
Yeah, so I think the major mission, I suppose, that really gave fantastic statistics on planetary occurrence rates was the Kepler Space Telescope. So that mission, which just observed many thousands of transits of stars and populated those diagrams I was showing, which had lots of dots on them showing planets of different radii at different distances from their star. Those kind of diagrams are populated by that Kepler Space Telescope mission, which was an extremely modest telescope compared to, say, like something like JWST, but that faint repeated dimming of the light of a star from a transit can be readily detected with fairly modest space telescopes. So that's been one of the most, the most consequential mission. Since then, the other data that's in there is, the other inspiring discovery from the perspective of understanding rocky planets is the TRAPPIST-1 system. So that system of 7 Earth-sized planets orbiting a star just 30 light years away. That was discovered by ground-based search, but then followed up from space as well. So those between them, because the TRAPPIST is such like a fantastic system to then study with instruments like JWST. Kepler gives us the statistics. The TRAPPIST survey gave us TRAPPIST, this remarkable system, and which then between them give us everything we need to then throw the big instruments like JWST, like the future giant ground-based, extremely large telescopes.
Thank you. Any other questions from the floor? 1 second.
Yeah. Something maybe for us amateurs. What's the most likely angle Earth will be hit by an asteroid?
Oh.
So if us amateurs are looking in the sky, what sort of band would we look at?
Oh, that's interesting. I think it is isotropic. I think ultimately it comes from, the impacts come from all directions equally onto the planet, but they're most likely to hit the surface at 45 degrees. I would like to say that the UK is blessed in being the most likely place to be hit by a giant impact. I think if it was going to happen, I think I'd want to be right at the centre of it. But I don't think we're special in that respect, sadly.
So with regard to impact, the main question is, what are the chances of being killed as a result of an asteroid impact? And as I understand it, it's balancing the fact that nobody has been killed by an impact so far, although a couple of people have been hit by small impacts.
A dog might have been killed, I think. That's alleged.
Yes,
an alleged dog death.
Yes. So the question is, it's a very low probability of it happening, but if it does happen, or something like the dinosaur impact, then it's going to kill everyone, right? So overall, if you combine those, it's been calculated by someone that the chances of someone dying in an asteroid impact are about 14 million to 1, which happens to be about the same chance as winning the national lottery. So the next time someone has a ticket and you say good luck, just have another think about it. Okay, if there are... Yes? Okay, well, one more.
Can I borrow the...
Yeah.
I've thought of something now. In the 1950s, before the space program really began, a scientist called James Lovelock studied the atmospheres of other planets in the solar system, and he didn't. I'm not sure quite what technique he was using, but he deduced that there was no biology, no signature in their atmospheres. And when NASA were preparing to launch the first interplanetary probes, he told NASA that they would not find life on Mars or Venus because of what his studies from the Earth. Can the same techniques be used to detect the presence or absence of biology on exoplanets today? Are they using that technique?
Yeah, so the Lovelock's insight was that biology sustains disequilibrium in Earth's atmosphere. So it sustains chemicals that, if left to their own devices, would react with each other, but are sustained together in the atmosphere because biology is constantly producing them. So it's a
signature, yeah.
Yeah, so it's not that any one gas on its own is peculiar. It's that the two things together would react and go away, but the fact they're still there means there must be constant large sources of them from biology, and that's a really beautiful insight.
I wonder if they could do the same thing at the distances to exoplanets.
Yeah,
they can. All right.
Well,
is that how we're going to discover, if we do, extraterrestrial life?
Yeah, so that idea has had a profound impact on the field and is recognised as a key way in which to identify life being active on a planetary surface, is sustaining the atmosphere in a state of chemical disequilibrium.
So it can be done?
Yeah, yeah.
Right. With today's technology, yeah.
In principle, yeah.
Right.
It can be done, yeah.
Okay, thanks.
Yeah.
Any more from Zoom? No. Okay. In that case, I'd just like to say, on behalf of everyone here and on Zoom, thank you very much, Oliver, for your presentation today and for answering our range of questions. I certainly learned a lot. It's not, I would say, an area that a lot of us know a great deal. So as I said, when I first saw your proposal for this subject, I thought, well, this is going to be interesting, and it certainly was. So thank you very much indeed.
Okay, well, thank you very much indeed for what a fascinating talk that was. And like Jerry said, in an area which is pretty well unknown to all of us. So that was absolutely brilliant. On behalf of everybody at the Hartford Astronomy Group, both live at the university and on Zoom. I'm sure we're very, very appreciative of the time you've given to come to our talk this evening, and what a fascinating talk it was. So thank you very much indeed, Oliver. Just a few closing remarks. I won't keep you long. First of all, I'd like to specially thank the team down there who've put tonight's presentation together, particularly for Jerry and to Martin for their presentations at the start. I'd like to thank Dan and Steve, the tech team, who put together a really brilliant production. I think there's some new shots that we got tonight, and I can tell you, looking at them from Zoom, they were really, really good. So thank you ever so much for that. And of course, for the admin, which goes on in the background, Tony and Dennis, Tony handling the membership issues, and Dennis volunteering to be the usher to show you to the seats, and for everyone who's made tonight's meeting possible. Thank you very much indeed. It's very much appreciated. Date for your diary. Hope you've all written down next week, 17th of May, and you're all going to come along to the AGM, aren't you? Aren't you? That was a deafening silence. Please do come along. It'd be lovely to see you there. If you don't make it to that, we'd like to see you on the 14th of June, when Helen Mason will be coming along and giving us a talk, Reaching for the Sun. You remember the sun? That's that bright thing that Steve manages to get pictures of. It'd be lovely to see a little bit more of it. For those of you at the university, do have a safe journey home. For those of you on Zoom, you can hang around and have a little chat amongst yourselves, particularly if you're new to the group. Do stay around and introduce yourselves and have a couple of words with us before we sign off. I'll officially end the meeting here, but those of us on Zoom, we will carry on. Thank you very much and good night.
Thank you.